And in case any of you were looking for it, I think I'll actually go back one slide here. Sounds like something just collapsed. Oh, I know what collapsed. It was a dog in the hall. Okay. Let's go on and get set up for the whiteboard, because that's where we'll be starting. Okay, and now I got to get this out of the way. Sort of not killing time, but just hoping some more students will show up before I start making announcements, because then I'll have to make them over and over and over again. But it looks like we've still got the 7, and that's all so far. So let's go over how it looks like the term will end. Today is, of course, the day you've been dreading all term, the last day of class. Okay? Now, I hope all of you saw it. I put out there the Chapter 7 test on Blackboard Message. I did that, can't remember when it was. It was either late Monday. I think it was late Monday. Okay, so hopefully you've had a chance to see it and maybe even get started on it. I think that'll have to be your last test. And unfortunately, we only had 2 tests this summer, which is very unfortunate but they lost us a week and a half by poor scheduling, and then they cut the term by another week and a half. So basically we lost 3 weeks of class out of a 10-week term. That's not very acceptable, but it's happened. We can't do anything about it, and I guess there were legitimate reasons why they did at least the latter, but the former was, to me, inexcusable. But they did it, so no reason crying over spilt milk. So what we're doing now, though, is probably the most important chapter in the course, because this is what you're going to be called on to deal with in other courses that follow this. So that's why I'm a little disappointed there's only the 7 of you here today. I'm afraid the others got their test and ran, but it's their loss. So anyway, for you guys, please try to get me your that last test in. If you can get it in today, that would be wonderful, absolutely wonderful. If you can get it in tomorrow, that would be great just as well. Tomorrow is technically the day when the final exams are due, okay? However, I will give you Friday, and I'll give you Saturday to work on them, and even Sunday, but I have to, absolutely, without a doubt, have to have them in by Sunday. If they are not to me by Sunday, and I mean at a reasonable time on Sunday, there's hardly any way I'll be able to get a grade entered for you, because we have to have grades in by noon on Monday. And if I have not gotten your exam in time to grade it on Sunday, and then Monday comes around and all these papers start coming in, there's no way in the 4 hours between 8 and 12 that I'll be able to get all the papers graded and all the things listed in Blackboard and all the things posted on your final exam, final grades. I just can't do it. It's just too much. I've been there many times before. You just can't. I can't. Things that come in on Monday or so late on Sunday I don't have a chance to grade them. That almost is going to be an incomplete. I can't swear it will be. If I can get it graded that Monday morning and get the things done, I will. But there's a real good chance anything that comes in late Sunday or Monday will probably wind up being incomplete until I can get it graded, and then the grade change. And I'll make the grade change just as soon as I can. I've got 5 classes. Okay, this is my biggest one, but another one is almost this size. So I've been getting, I'll just show you. Last night and this morning, I probably printed the vast majority of these things. I got a few things graded, but basically all morning long and last evening too, I've been doing almost nothing but printing. There's been some emails I had to respond to and send things and variety of things like that, but almost all of what I've been doing is printing, and I'm not through printing. Okay, I ran out of time before lunch today to get the last few things printed, and I have a feeling by the time the 2 classes I have now, back-to-back classes, are over this evening, I'll have a whole bunch more to print besides the ones that I left off printing this morning. So as soon as I get all the printing done, then I get to grading. And as soon as I get all the grading done, then I'll put the grades in Blackboard. So if you have received from me an acknowledgement that I've received either a research paper or received a test or something like that, that means I have it. It's printed. It may not mean I've graded it. I may have graded it, but I just haven't had a chance to put it on Blackboard because all this stuff is coming in, and I swear everything in that stack I just showed you has come in within the last week. Okay, that much has come in just in the last week. So it's almost a losing battle. Okay, I won't lose it. I'll come through, but I'm going to be grading from now on, trying to whittle down that stack. And I've still got more printing to go. So that's how things are sitting. Any questions before we get started on the math today? All right. If you haven't turned in that research paper, please get it in. That is almost immediate. I need that very, very soon. Okay. If you haven't gotten the first test in, please get that in, because you now have the second test and there's just no time to be doing a paper and 2 tests in the short time you've got left. So please get the first 2 in so you can focus on the latter. All right, any questions? All right, we're in Chapter A, Integration Techniques and Improper Integrals. We're only going to do the integration techniques part, and we're in 8.2, Integration by Parts. Okay, and hopefully you were here last time and got an introduction to it. If you weren't, pick it up from what we're doing now, because don't have time to go back and do it all. So go over all the details. So let's see if the pen will ever show up where it's supposed to. Well, maybe if I turned it the right way it would. Okay, there it is. All right, here's what we're asked to find: the integral of x squared sine x dx. Okay, now you probably won't find in any integration table or anything else how to integrate this thing. Okay, you might actually find something that's fairly close and that would work, but it's a fairly reasonable process to determine how to integrate this. Okay, it's a product. That's a dead giveaway. It's a really good chance integration by parts is going to work, because integration by parts is based on differentiating by the product rule. Now, it's not the same, but it's based on it. You have a product here. Now, one part of the product is x squared and the other part is sine x. The dx can go with either one of those. That's our determination. Now, one part of that product you're going to differentiate. The other part of the product you're going to integrate. So most of the time, not all the time, but most of the time, when you differentiate, your function gets simpler. Most of the time, when you integrate, your function actually gets more complicated. Especially if it's a power rule, you bump it up a power and divide by a fraction. Okay, that power. So what we look for to see is the part that you want to differentiate. You want to make sure it does get simpler. Okay, well, x squared definitely gets simpler if you differentiate it. Sine x doesn't get any more complicated if you differentiate it. Okay, on the other hand, x squared gets more complicated if you integrate it, whereas sine x Doesn't get any more complicated if you integrate it. So, obvious choice, differentiate the x squared, integrate the sine x. So how we go about saying that is let u, the part we're going to integrate, be the part we want to integrate, x squared. And dv, the other part, the one we're going to integrate, sorry about that, is equal to sine x dx. Okay, now notice here, the dv here gets the dx there. Always the d's go together. The d doesn't go over here with the u because you've got to differentiate that. So then your then line, anytime you have a let, most of the time you're going to follow it with a then. Du is equal to, differentiate that, 2x dx. Remember, the d's go together. Okay? Now, we're going to integrate these two. Okay? So to speak. When you integrate a dv, you just get a v. Okay? Antiderivative. Antiderivative of a derivative is whatever the function is, which is v. Now, the antiderivative of sine x dx, hopefully you know this, is minus cosine x. Why? Because the derivative of cosine is minus sine. Since that's a positive sign, you have to have the minus with the cosine. Notice you don't have a d now anymore. Okay, so now you've broken it into parts, integration by parts, and you've done this. Now, how does that lead to a solution for the integral we have here? Well, this is where the, whoa, here comes somebody. I can't see who it is. Jesus. So let me get a Jesus in here. And there, I've got him in. All right. Now we're up to, I think, 8 students. Okay. So this is where, Jesus, where, if you can hear us now, we're on page 526, Chapter A, Integration Techniques and Improper Integrals, Section 8.2, Integration by Parts, Example 4, near the top of page 526. If you don't have a book, here it is. Okay. So we're integrating that. We're going to do it by parts, and here's how the integration by parts does. If you had started with the product of two functions, I'll tell you what two functions they are. These two right here, u times v. Then when you differentiate that, it's u dv plus v du. Okay? Well, if you're integrating the derivative of the derivative of uv, its antiderivative would be uv. So that's where we start. You do the u times the v. That's this one times that one. So the first part of this is x squared, that's the u, and the v is a minus cosine, so I'm going to put the minus out front, minus cosine x, done. That's all. Okay. I meant to say this earlier. When you do this integration here, if I can get my pen to show up, that integration, never put a plus c there. You'll do that at the end if you need it. Okay? So there is your u times v. Okay? And then what you're left with is a minus the integral of the bottom line down here, the v du. Okay? Well, that would be a minus times this minus is going to make that a plus. So that's where the plus comes into play. And you've got a 2 here that you really don't need in the integral. So we're going to pull it on the outside. And then what you have is x cosine x dx. Well, guess what, team? We still have a product in our integral that we don't have a way to do. So guess what? We do it again. Okay, for this integral now, if I can get the pen to show up, here it is. For this integral, we do it again, and if you're okay with it, I'm going to use the same letters, it's just a different integral. Let, I'm going to go the same way too. U equal x, it got simpler the first time, it'll get even simpler this time. And dv, what's left, is equal to cosine x dx. Remember, the d's always go together. And then what we'll do is differentiate this one. Du is equal to, well, derivative of x is just dx, or 1 dx if you wanted to write that down. There's no reason to, it's just dx. If you integrate this one and this one, this will just be v, and then that will be antiderivative of cosine x is sine x. Don't do a plus c on this, okay? Now, we got to go back and be sure we don't forget anything. So this first integral here, this is what, I'm not going to rewrite it again, but this is what comes down here. And this is equal to what we had before, a minus x squared cosine x. The pen's not doing all that well, but it's readable. Plus, come on, here we go, okay, plus 2, okay. Now, what do we do next? Same as before, the u times v, that's x sine x, so it's 2x sine x minus, okay, the bottom line, the v du, the integral of that. Now remember that 2's in front of this too, so don't forget that 2, times the integral of what you have left here. Well, that is v sine x du, which is dx. Now that one we can do, okay? So this integral we started at the very beginning, somewhere over here, okay, it's going to be minus x squared cosine x. I found if I slow down my writing, the pen has fewer problems. Plus 2x sine x. Now we'll do this one. Minus, what's the antiderivative of sine x? Minus cosine x. So that minus becomes a plus 2 cosine x. And here's where you put your plus c because it's an indefinite integral. Okay, that's the only plus c you need to put in. All right, so let's see how the book wound up. The integral of x squared sine x dx is equal to minus x squared cosine x plus 2x sine x plus 2 cosine x plus your integration constant c. Very good. Any questions on that? That's one you just have to do a couple times. If that power of x had been 3 or 4 or 5, you just have to do integration by parts that many times. Now, a little bit later, if we get to it, you'll find there is sort of a shortcut for that, and we'll go over that later too. But this is not so bad that you need a shortcut for this one yet. All right, if there's no more questions on example 4, let's move on to example 5. Any questions? All right, I'm going to clear the drawings. Now, Jesus, your Lights on, but your microphone's off. Were you trying to say something? Maybe not. Okay. All right, so I'll clear the drawings. And let's go to example 5. Here we have an integral. This is such a pain in the neck. I have the computer takes up almost all the desktop, so I have to put the book in my lap when I'm trying to do the opposite page. Here is the problem. We're trying to integrate secant cubed x. This is such a pain in the neck. Okay, secant. Now notice I said I found out if I slow down the writing, it improves the pen performance, but when I do that and get it too slow, then it checks out on me like it just did. Secant cubed x dx. Okay, now this you need to recall some features of good old trigonometry. Okay, first, that doesn't seem to be a product of any two functions. Well, it is, though. It's a product of, and I think I'll go on and write it down this way. That's the integral of secant x times secant squared x dx. Now, actually, differentiating secant x is not a particularly pretty sight. Okay, it actually does look like it gets more complicated, but not a lot more complicated. If you were to differentiate secant squared x, you'd have the same problem plus your, when you got to the chain rule part, same problem, but then you have the 2 secant x in front, so that's even more complicated. However, okay, here's the big question. These shows how much you remember of your trig differentiation. Is secant squared x the antiderivative for anything? I'll give you a hint. Secant x is not. Is secant squared x? I can tell all of you are trying to answer it at the same time and you're getting all clogged up there. So I'll remind you of this, that the derivative, get out of there, okay, derivative of tangent x, this is so aggravating, stupid thing. Okay, I don't know if y'all could see that at all, but it messed up my screen. Derivative of tangent x is nothing other than secant squared x dx. So that's a good suggestion, that to integrate, where is it? Yeah, integrate this part, differentiate that part. So that's what we'll do. Let u equal secant x this is aggravating, secant x and dv is equal to secant squared x dx. Okay, then usually follow let's. Du, all right, now you have to remember this one. Anyone remember what derivative of secant x is? Rather a strange one, but true. It is secant x tangent x. Like I said, it actually gets a little more complicated. Tangent x dx, remember the d's always go together, and we've already said that v would then be simply tangent x Okay. Now, with that in mind, what this integral is here of your, that's what we started with, it is going to be equal to the functions themselves, the uv, which is secant x tangent x, minus, remember that's always a minus, okay, the integral of the bottom line here, these two, and that will be secant x times tangent squared x. Oh man, dx. Okay, now the question is, what do you do with that? Now here the key is recognize for what it's worth your trigonometric identity that's here. Okay, and let's go off to the side just like we did before, and remember that I'll write it out. Let me do this. Tangent squared x plus 1 is equal to secant squared x, Pythagorean identity. Okay, so that makes tangent squared x equal to secant squared x minus 1. Now this is for you to see and remember this and know this is going to be the way you're going to do the problem. That's asking a lot. Okay, they sort of threw this one in here as a pretty tough example, and of course they didn't put it on the PowerPoint, which they usually put the easy ones on the PowerPoint, leave the tough ones for you to figure out yourself. But it's in the book, so there it is. So then we're going to rewrite this equation, if I can find my pen again. I think I'll rewrite it here. This will be minus the integral of secant cubed x, which we've seen before. I'm going to put that with its dx here, because I'm putting secant squared x minus 1 instead of tangent x, and then it's going to be minus, the minus is going to be plus, because I had a minus out front, it's going to be minus and minus is a plus, and the second integral here will simply be secant x dx. Okay, now I skipped some steps there, and I hope you don't mind too much. I put this thing right here in for tangent x, okay, and then I multiplied it, and secant x times secant squared x is secant cubed x, and secant x times a minus 1, a minus in front and another minus makes it plus secant x dx. Okay, now this is sort of an interesting situation. I'm going to tell you right now, don't do anything with this. I'll tell you why in a minute. Now, the other question is, what in the world do we do with the integral of secant x? Now, we had it before, back when we first started integration of trig functions. I think this was in chapter 5. Okay? And what the integral of secant x is, and it's in your book on page 527, next to the last line there, it's the log of the secant x plus tangent x, of course absolute value. So this part here, if I can get the pen to agree to come down here, this part here is going to be the log natural log of absolute value of secant x plus tangent x. That's something you can look up in a table if you don't remember doing it, but that's what it was, and we did it way back. Okay. Now, I think I'll go on and put my plus c in there because, believe it or not, we're through integrating. Okay. But wait a minute, you say, here's still an integral here. But this integral is the same as this one over here. And remember, this is the equal sign here. And remember, you have a secant x, tangent x here from the beginning. Okay. So what we're going to do is add this to that. So it's going to basically wipe out this and make two of these. Okay. So now we have two of those is equal to what we have left. And then if we divide by 2, we get our original problem, the integral of secant squared x dx. That's what we were looking for. And now we have it as 1/2 secant x tangent x okay, plus 1/2 the log, natural log of absolute value, secant x plus tangent x. And then we have our plus c. Now, I probably should have waited on the plus c till this step, because technically it's 1/2 c. Hey, c is a constant, 1/2 c is a constant, it's just a constant. Okay? Let's see how we did. The integral of secant squared x, I'm sorry. I wrote it as a square when it's a cube. Okay? Sorry about that. Integral of secant cubed x. It's a cubed up there, it's a cubed right here. Integral of secant cubed x dx is equal to 1/2 secant x times tangent x plus 1/2 the natural log of the sum, absolute value of the sum of secant x plus tangent x. And then you have your plus c. All right. Any questions on that? All right. One more that they don't do, and again, a little bit different and maybe even slightly involved problem here, using what we did at the end of chapter 7. And that's going to be finding a centroid. A machine part is modeled by the region bounded by the graph of y is equal to sine x. So I'm going to try to get my pen over here. There it is. Y is equal to sine x. Okay. And the x-axis. And you're going from 0 to pi halves for x. Okay. So the x-axis is the other part. And the x-axis is where y is equal to 0. So rather than writing x-axis where y is equal to 0, and then you're going from 0 less than or equal to x and less than or equal to pi halves. Now everything's positive there, except y equals 0, of course it's 0. But the sine x is positive. It starts at 0 and goes up to 1 at pi halves. I'm sorry. I've been having a lot of, I don't know what you call it, drainage, but issues. And I think I told you all this on Monday. Probably stemming from the weekend when we were out in the heat, out in dust, and out in a lot of pollen and stuff. So I'm still clearing my head. Let me kind of get something to wet my whistle, try to break up some of the congestion that I feel. Okay, now I wish they had, I'm going to show you the picture, okay? I think I'm going to have to wind up drawing it too, but this is what my drawing is supposed to look like, if I can find it. There it is. Okay. I don't know if you can see it, but there is the sine x from 0 to pi halves. Of course, the x-axis is where it is. That's the part that we're talking about. The machine part is modeled by the region bounded by the graph of y is equal sine x, x-axis between 0 and pi halves for x. And what we want to do is find the centroid of that region. Okay. And again, like I said, I think I'm going to have to sort of draw it to make things make sense. Otherwise, I'll be doing a lot of arm waving that might not. I'm going to try to draw it freehand now so I don't have to mess with the lines. The sine curve does something like that. Okay. This is pi halves. Okay, and that's not a very pretty sine curve. But now we're talking about the centroid of this plate that goes from 0 to sine. This is sine x, supposedly. Okay, this is where the value is 1 here. Okay, that pi halves there. And we want the centroid of each of these regions. Okay, and that is a pain in the neck. Okay. Okay, somewhere in there is a centroid. My dot didn't come out in the middle where I wanted it, but you got the general idea. Okay, now it seems pretty obvious we got to do our dx's here. And if you remember how the centroid problem works, it's the center of mass of this little region here, which is exactly sine x over 2. It's the average of those two, sine x over 2. Remember, we're calling this a well, they didn't call it, but we're treating it as if it's a lamina. Okay, so the center of gravity would be the center of it. Centroid would be the center of that. Okay, so it's the all right, let's start with the x bar. Okay, we'll do y bar in a minute. Okay, the x bar would be then, let's see, probably a good idea to start with the mass of it, which you really don't need to do mass, you just need to do area. Well, the area of it is simply the integral from 0 to pi halves of sine x dx, because the area is just the height of that bar, is the height, which is sine x, times the thickness, which is dx. So that's the area. Now your numerator of this is is basically that same thing that's going to be in it, the area of that, but we're going to multiply that by the they call it the moment with respect to the y-axis, which is just going to be your x, right? That the centroid of that, I guess I wish I could get my pen to stay still right there, is going to be the moment with respect to the y-axis. The distance from the y-axis is just x. Okay, so that's going to be x sine x. This is so bad. Dx. Okay, and again that's going from 0 to pi halves. So that's going to be the x bar. The y bar, on the other hand, is the moment with respect to the x-axis, and that's going to be 0 to pi halves. Okay, and that will be the average value there. That's what I started talking about, but I decided to go back and do the y bar first, x bar first. Okay, so that's going to be the average of those two is sine x over 2. Okay, and then times sine x dx. The average value is halfway up it, okay, and the denominator is the same, integral from 0 to pi halves. Sorry that the writing is so terrible here, okay, of sine x dx. Okay, now they go on and do the area first, the integral of sine x dx. So I wrote it all down that way just to remind you how it looked. Much easier just to do it if I can come over here and do it. That area right there, that's your denominator here and here, okay, is the integral from 0 to pi halves of sine x dx. Well, yuck. Okay. Antiderivative of sine x is minus cosine x, remember? And you're evaluating that from 0 to pi halves. Okay? Now, cosine at pi halves is 0. Minus minus is plus, the cosine of 0 is 1. So guess what? That area, and we're assuming density is 1, so that would be that, is 1. Okay, so that makes the whole problem pretty easy, okay, because your denominators here are 1. Probably should have done that first. These denominators are just the number 1. Okay, so what it gets to be is, here is, for your x bar here, you have a problem a lot like we did integration by parts. Okay, it's the integral from 0 to pi halves of x sine x. dx. Okay, now let u be, hopefully you recognize this, your x, and dv be sine x dx. Okay, then, I don't have much room here, then du is equal to dx, and v is equal to, remember, if you integrate sine x, we just set it up here, you get a minus cosine x dx. Okay? No, I'm sorry. Minus cosine x. Okay. Don't ever put a plus c on that. So then what is your solution for this? This integral we're looking for, this one right up here, this one right here, is going to be uv. Now I'm going to erase some stuff if that's okay, because this is so messy. Okay, so let me erase this drawing. It's ugly enough. I think we got all the benefit out of it we could get. I'll really kick myself if we don't. Okay, we've already done that one, and we know that's equal to 1. So no reason to go back and redo that. We know it's 1. Okay, so back. Now, this integral here is going to be uv, so that's minus x cosine x, that's the u times the v. That's evaluated from 0 to pi halves. When you have limits there, you evaluate that too, even though there was no integration involved. It's part of an integral problem. And then you have a minus, but then you have this minus, so that's going to turn into a plus the integral of the bottom line here, okay, which is cosine x dx. And that's going from 0 to pi halves. Okay. Now, I think we've already, well, no, we haven't quite already done this. If we do this, what we get, that first one, is going to be a minus pi halves, when you plug pi halves in for x, minus pi halves times cosine of pi halves. Cosine of pi halves is 0. That doesn't even exist then. Minus, the minus makes it a plus 0 times cosine 0. Well, that goes away, okay? So guess what? That first term doesn't contribute a thing. All you're left with is this, and what is that integral? If we can get it to come down here, that is going to be antiderivative of cosine x is sine x. And sine x is evaluated from 0 to pi halves. And sine of pi halves is 1. And sine of 0 is 0. So, oh, I wish I had left the graph up. I'm going to sort of draw it again. A really lousy rendition of it. Remember, this is going from 0 to pi halves. Pi halves is a little bit further than 1.5. So 1 would be right about there. Okay, so your centroid is going to be somewhere in there. That's the x value. Let's see what the y value is. This integral down here, and it's really messy. Remember, the denominator is 1. So this is the integral from 0 to pi halves of, and you have a 1/2 from this 1/2 here, sine squared x dx. Okay. Now, that's something we don't typically know either. Okay. Now, they actually started with their y bar. Okay. And you have to go to a another trig identity. Okay. And this is one that you probably don't remember quite as well as you may Pythagorean identities or things you use all the time. If you have this text and go to the front inside cover of the book, okay, there's a page. The first page there is sort of cardstock page. It actually is perforated in my book anyway. On the front side is derivatives and integrals. We don't want that right now. Flip to the second side of that, and that's trigonometry. And that's what we want to look at. Okay? And there you'll see on the right hand side, underneath the circle, the unit circle with all the pieces to it, you have what you call the double angle formulas. Okay? And then right below that, and this is where you get these, is the power reducing formulas. And that's what we're going to use. Sine squared u is equal to 1/2 of 1 minus cosine 2u. So this is going to be, and remember I said there's a 1/2 in front, We already have a 1/2 here, so this is going to make it a 1/4. That's where the 4 comes from. The integral from 0 to pi halves. Okay, you've already taken the 1/2 out front, and what you have now is 1 minus cosine, not of x, but 2x. Okay, and then dx. Okay, the thing in the book was dealing with u's, we're dealing with x's. So that's where you get that integral. Now that's a fairly easy integral to handle. If I could get my pen to come over here and handle it. Okay, all right, I'm going to come down here to handle it. 1/4 is out in front. Okay, this is our y bar, remember, times. Well, the antiderivative of 1 dx is x evaluated from 0 to pi halves, so that's going to be pi halves. That's the antiderivative of 1 times dx is dx. Okay, it's x evaluated from pi halves to 0 to pi halves. That's just going to be pi halves. Minus, okay, what is the antiderivative of cosine to x? Well, the antiderivative of cosine is sine, okay, positive, so that's going to remain a negative there. And you'll have a sine of 2x, but then you undo the chain rule by dividing by 2 from that one. Okay, all right, and this you're evaluating from 0 to pi halves. Okay, well, twice pi halves is pi, and sine of pi is 0. Okay, and sine of 0, 2 times 0 is 0, sine of 0 is 0, so basically this does not contribute a thing. So what do we have? Pi eighths is the y. Y bar is pi eighths. Now remember, pi is just a little bit more than 3, so this is a little bit more than 3/8. So if this here is 1, that would be 1/2, and 3/8 would be something about right there. Yuck! I hate this thing. Okay, so it'd be somewhere right, and there was our x, so here it is somewhere right about there. Okay, that would be your centroid. Closer to the bottom, I put it too high. Closer to the bottom, the x-axis, than it would be to the top of that, so it's somewhere down here somewhere. Yeah, that's a more realistic place. Okay, and about 2/3 of the way out, because it's, you got more mass on this end than you do on this end, so it's 2/3 of the way out here approximately, and you got more mass down here than you do up here, so it's more closer here. So that's what we get. Pi eighths is the I think I said that wrong. Whoa, 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 here's James Mullins. Let me get James here. Okay, James is here. Good deal. Okay, I think that gets us up to 8 students. 1, 2, 3, 4, 5, 6, 7, 8, 9. We've actually lost somebody too, so don't know who that was. Okay, so I was saying that wrong. I was saying 3/8 pi. It's pi eighths. Pi eighths would actually be somewhere closer to, this is pi halves, pi fourths, pi eighths is actually down here some. Yeah, get out of there. Somewhere down here, so it's pretty close to the x-axis. Okay, those top two were not right. That one is. So pi eighths is the y bar, and 1 was the x bar. Okay, it's at 1 pi eighths. So the x bar, y bar, that's the centroid, is equal to 1 pi 8. Exactly what we got. All right, now finally, any questions on this before I leave the whiteboard? Okay, I'm going to clear it and go back to 8.2. All right. And this is what they say at the top of page 528. Oh, let me go on and expand the slideshow here to current slide. Okay, as you gain experience in using integration by parts, your skill in determining which is the U and which is the DV will get better. Don't worry if you have some false starts. That's part of the game. The more practice you do of it, the better you'll get at guessing, but you'll still have some, nope, that won't work, let's try it the other way. So the next summary, it's sort of a table, lists several common integrals with suggestions for the choices of U and V. So let's see, here's the summary. Common integrals using integration by parts. If you have an integral that's integral of x to the n e to the ax dx, okay? Now, they don't say this, but in reality that n had better be positive. If that n is negative, you really have big problems, okay? You want that n to be positive, okay? So if that's a positive n, it could be 1, it could be 2, it could be 7, it could be, any positive integer, okay? Then obviously taking derivative of this is going to make it simpler, one step at a time, and integrating this isn't going to make it much more difficult. Yeah, you get some 1 over a's every time you integrate, but those are easy to deal with. Same thing if you have sines and cosines. Taking the derivative of this part, let that be your u, let this be your dv, because integrating a sine gives you a cosine, plus or minus, okay, and integrating a cosine gives you plus or minus sine. So every time you do it, you just are going to go back and forth between sines and cosines. And again, you get 1 over a's every time, but those are just constants. They're just numbers. That's fine. The function doesn't get any more complicated. So integrating the first part, so let the u be the x to the n and the dv be either e to ax dx, sine ax dx, or cosine ax dx. Okay. Now, not so with logs. If you have a log function, okay, you don't want to be integrating that. I don't even know how to integrate that. So in this case, you have to go the other way. Let this be your dv, x to the n dx. Let this be your u, because what's the derivative of log x? 1 over x. So you basically knock out the one you just increased it by, and now you have a power rule and you can go with that. Okay? It's kind of the same argument with arcsine. Most of the time I don't mess with arcsines and arctangents, but if you did have them in there, if you remember, there is usually a denominator that has powers of x in them. In other words, you don't have anything you can take an antiderivative of arcsine or arctangent, so you basically have to differentiate it, okay? And they're not too bad. Messy, but not too bad. So in those cases, your log x, your arcsine x, and your arctangent x, or ax, those all become your u, okay? And your dv will then be this thing that does get a little more complicated, but not too badly. Sorry. All right, the third kind. For integrals of this form, that you either have e to the x and sine bx, e to the ax sine bx, or e to the ax sine cosine bx, guess what? It doesn't really matter. They say let u be the trig function, dv be the e function. Yeah, I prefer it that way, but it really doesn't matter because both of them just go back and forth when you take derivatives or antiderivatives, okay? They just go back and forth. It's the reason I would say I use this one, let u be this. I know my differentiations better than I know my integrations, antiderivatives. I usually will get the signs right going one way, and I have to stop and think about it going the other way. Whereas there's no sign change at all with the e to the ax when you're integrating. So go with that. These, when you're differentiating, you get multiplied by b's. When you antiderivative, you divide by the a's. So that doesn't really matter. Okay, so those are their suggestions. But again, now, if you have multiple of these to do, be sure, if you start doing this and for some reason you have to do it again, don't go and reverse it, because then you go back to the original problem. Always keep going with this being your u and that being your dv. That's true on all of them. All right, in problems involving repeated applications of integration by parts, a tabular method illustrated in example 7, I told you we were going to get here, can help to organize the work, and that method works well for integrals of the form, and this is what I was saying, when you have repeated integration, if that n is a very large number, doesn't have to be really large, but just anything more than 3 or 4, okay, and they can easily be, this is going to be easy antiderivating it, right, and that, and this will be pretty easy going the other way. So here, and by the way, you can go to larsonCalculus.com and see an interactive example, interactive version of this type of example 7. Let's see if they show it. Yes, they do. Good for them. Okay, now here's what you're going to do. Okay, when you have the sign there, okay, and they're going to keep a very simple low n, 2, okay. All right, now what they show at the beginning is you put your signs down, and you always alternate the sign, because every time you do an integration by parts, the first is positive, the next is negative, okay, positive, negative. So that's what they show first. Oh yeah, I'm sorry, I don't know what that was about, but I started to write on the screen. I can't do that. Here we go. Let's see if we can just do it here. The signs will be plus, minus, plus, minus, plus, minus, plus, minus. We're not going to need all those. Okay, that's the first column. The next column, you put the you start with the what you're going to let you be your first u, and that's x squared. So that'll be x squared, and then you take derivatives. I don't know why it did that line there. Derivative is going to be 2x. Derivative of that is going to be 2. Derivative of that is going to be 0. Stop. We don't need those others at the bottom. Okay, the third column, we put the v, v prime, the dv, and in the very first, that's going to be your sine of 4x. Okay, all right, and then you're going to integrate every one of those. Now, don't think this sign over here is taking care of the integration. No, you do the sign. When you integrate, or antiderivative of sine is a minus cosine, and there, I don't know why it does that, of 4x over 4. Remember the chain rule, you have to divide by it. The next one, when you take the antiderivative of that, you'll keep that sign, sine of 4x, and now you're dividing by 16. I don't know why it's doing that. Okay, and then we'll do it one more time, and the antiderivative of sine is a negative cosine, so that's going to change this back to a plus cosine, there it did it again, of 4x, and this time it'll be over 64. Okay, now that's our setup. Okay, and here's what we do, and unfortunately those lines have shown up there, so you go across to this one but down to this one, and there it did it again, across to this one but down to that one, across to this one, down to that one, and then you would be going across to this one, but that's a 0, so you're not going to go any further. Now you write out your answers. Okay, and that's all you do. You get, because this is a yuck, where is the pen? There it is, plus x squared but times a minus cosine, so you get minus x squared, and there it did it again, I don't know why, minus x squared cosine 4x over 4, and then you have a minus 2 but another minus, so that's going to give you a plus, and you're going to have a 2 up here but a 16 down there, so it's, I'm going to write it as 1/8 because I don't like having to write all that under it, x sine of 4x, and then you have a plus a 2 and this, well the 2 will make that a 32, so that'll be a plus cosine 4x. There it did it again, 1 over 32. Okay, so there's your answer. Negative 1/4 x squared cosine 4x plus 1/8 x sine 4x positive 1/32 cosine cosine of 4x. And then don't forget, because that was an indefinite integral, you have to put a plus c. Okay, let's see, that integral would be negative 1/4 x squared cosine 4x plus 1/8 x sine 4x plus 1/32 cosine 4x plus c. Got it. Alright, now that's how we did it, with lines going all over the page, and I don't know why, and I can't erase that, so just ignore that. And what we'll do, begin as usual by letting u be x squared, dv be sine x 4x. So put u's here in the first column and dv's here. Okay, these are all supposed to be on the same line. Okay, and start with plus minus plus minus plus. Okay, and then start taking derivatives going down here, 2x to 0. Okay, and start antiderivating going down here, minus 1/4 cosine 4x minus 1/16 sine 4x plus 1/64 cosine 4x. And then here's the key, go across the plus to your u, but then go down 1 to the dv, because you got to get u dv, not that one but this one. Remember, it's uv and this would be your v, so uv, and then it's minus this one times that one plus this one times that one minus 0, stop there, make that a plus c. Okay, that's actually what happens. Okay, and that is what gave you then, solution is obtained by adding the sign products of the diagonal entries. The integral of x squared sine 4x dx would be minus 1/4 x squared cosine 4x plus 1/8 x sine 4x plus 1/32 cosine 4x plus c. Alright, that is, I'm pretty sure, the last slide in the section. Okay, so let me give you some homework exercises to practice on. Any of the odds 5 through 9, they're all at Calc Chat. 5's at Calc View. Either 11 or 13, both at Calc Chat. 11's at Calc View. Any of the odds 15 to 33, they're all at Calc Chat. 15's at Calc View. Either 35 or 37, they're both at Calc Chat. 39's at Calc Chat. It's a slope field, and so is 41. Now they say you might need a graphing utility or something like that. If you do and you don't want to mess with it, you don't need to mess with it. Okay, then any of the odds 43 to 51, they're all at Calc Chat. 45's at Calc View. Any of the odds 53 to 57, all at Calc Chat. 55's at Calc View. You can explore doing 59 and or 61. They should both be at Calc Chat. You can do either 63 or 65. They should be at Calc Chat. 67 should be at Calc Chat. 69 should be at Calc Chat. And any of the odds, these are proofs now, 71 to 75. They should all be at Calc Chat. And then using formulas, these were the ones like we just did, any of the odds 77 through 81. They should all be at Calc Chat. And now they say you need a graphing utility. You can see if you do or not. Either 83 or 85, they should both be at Calc Chat. And then either 87, 89, 91, they should all be at Calc Chat. 93 should be at Calc Chat. 95 should be at Calc Chat. 97 and or 99 should be at Calc Chat. Any questions? All right. Now, when I looked before, I had pulled up okay, I think we already checked on that. Pulled up, there's 8.2. Hopefully this will be 8.3. No, that's still 8.2. Why it has those twice and not the other, I don't know. So I think what I have to do is come back here. Let's see. Oh, let's do this. Let's just, okay, that's making a lot of noise. Let's close this for now. Okay. I don't think I need 8.2 anymore, so let's close it. Okay. Now sharing is stopped for a moment, but let me get 8.3 up. There it is. Okay. And then let's go back to our sharing. And I do not see there it is. I bet you that's it. Let's see if it is. No, but we'll do it this way. If they want us to do it this way, we'll do it this way. Okay. There it is. Okay. Boy, this is not an easy thing to navigate. All right, and we'll start this one from the current slide. Okay. Now before we get going here, let me do a couple of things. You can't see this, but I have a toolbar right smack on the area we want to look at and talk about. So I'm going to get rid of it. So here we have Chapter 8, Integration Techniques and Improper Integral. Again, I'm not going to get the improper integrals, just integration techniques. 8.3, for some reason it won't advance. Click on the slide, now it'll advance. Are trigonometric identities. Now, believe it or not, we have actually already done some of these, but we're going to do quite a few more. So objectives here are to solve trigonometric integrals involving powers of sines and cosines. We'll solve trigonometric integrals involving powers of secants and tangents. And then we'll solve trigonometric integrals involving sine cosine products. Now, we might get that far. We'll see. Okay, so let's start with integrals involving powers of sine and cosine. In this section, you'll study techniques for evaluating integrals of this form. Integral of sine m to the mth x times cosine to the nth x, and secant to the mth x and times tangent to the nth x, where either m or n is a positive integer. So one of them could be negative, but not both. One or the other, m or n, has to be positive. Has to absolutely be positive. If they're both negative, you kind of almost have to hang it up because we can't do those. Okay, so find antiderivatives for these forms. I need more water or liquid of some nature here. Drinking all this, I'm probably going to have a bladder break later, but for some reason not yet. Okay, to find antiderivatives for these forms, you try to break them into combinations of trig integrals to which you can apply the power rule. So we're going to be applying the power rule, but not to x, to trig functions, either sines, cosines, secants, or tangents. Don't worry, we're not going to worry with cosecants or cotangents at all in this endeavor here. Okay, so what if you had this one? Sine to the fifth x times cosine x, okay, dx. Well, guess what? A u substitution will do perfectly fine there, okay? And why? The most complicated part of that is the sine raised to the fifth. So take the innermost part of that, which is sine. Let u equal sine x. Then du would be, what's the derivative of sine x? Cosine x dx. There you have your du. So then you would have u to the fifth du. That's just a simple power rule, okay? So that would be u to the sixth over 6 plus c. Go back and plug in u is sine x, so it's sine 6th x over 6 plus c. Pretty easy. Now, what if you had sine to the mth x? That could have been a 5, m could have been a 5, but cosine to the nth x, this time not 1, something greater than 1. Well, now you've got to do some more fiddling, okay? So to break that into forms in which you can use the power rule, remember these things. Number 1, sine squared plus cosine squared is equal to 1. That's your basic Pythagorean identity you use all the time. Never forget that, okay? And we'll see how we use it. Now, actually, it's used to come up with this form. And this is the form we saw in one of the last examples we did. That sine squared x was 1/2 of 1 minus cosine 2x. But on the other hand, cosine squared x is 1 plus 1/2 of 1 plus cosine 2x. Now, you may not remember how you get those, but basically half of what you were using there you got from this part here, sine squared x plus cosine squared x equal 1. The other half you got from your cosine double angle formula, which is cosine of 2x is equal to cosine squared x minus sine squared x, and then either by adding or subtracting those together, that's how you get these, okay? Now, so here's the guidelines for evaluating integrals involving, and we're starting with sines and cosines. Now, when the power of the sine is odd and positive, pull out one sine factor, convert the remaining factors to cosines, expand and integrate. Okay, now that is fine. There's no reason just to do the sign, but if either the power of sine or cosine was odd and positive, you could have done it to either one. Okay, but they say if sine is odd, work with that one. Okay, now here's part of the reason for that. You pull out the 1. Okay, this is obviously an odd power now. K is any integer. 2k is going to be an even integer. 2k plus 1 will be an odd integer. So if the power for sine is odd, and it doesn't matter what the power for cosine is, forget that for now, then pull out one of those, and that leaves you sine squared x raised to the kth power, okay, times cosine nx, whatever that is, it doesn't matter, and here's that one you pulled out, sine x dx. That's going to be your du ultimately, not there yet, but then take this, sine squared x is 1 minus cosine squared x raised to the kth power. Now you just expand that binomial, okay? It's kind of a pain in the neck, but it's not hard, okay? And then you're multiplying that by cosine nx. Doesn't matter. This will be a power of cosine. That will be a power of cosine. All of them are multiplied by the derivative of cosine. So you got it. Now, the one issue with it is it's going to be a minus, okay? And that's why I kind of like to do the cosine first, but they don't, you know. When the power of the cosine is odd and positive, save one cosine factor, convert the remaining ones to sines, and then expand and integrate. So now it doesn't matter what the m is. Cosine's odd, meaning, say it was 7, this would be 2 times 3 plus 1. 6 plus 1 is 7. Pull one of those out, and that'll going to be ultimately a du, and then this will be a sine mx. This is going to be a cosine squared times k. Well, remember here we say cosine squared. We'll get to that, 2 times 3. So the k happens to be odd. It doesn't matter what it is. Excuse me just a second. Having these ear things on all the time makes my ears itch. Okay, so this is some power of 1. This is 1 minus sine squared, and this is a sine m. Expand that, raise that to the 3rd power. Now if you don't remember Pascal's triangle, go back and see Pascal's triangle. That makes doing these things pretty easy, okay, almost fun, okay. But keep that cosine x, that one that you pulled out to make this even, keep that one out there, and that becomes your du. Now, what if the powers of both the sine and the cosine are even and non-negative? Okay, well then what you do is repeated use of these formulas. The second one we saw, sine squared x is 1 minus cosine of 2x over 2. Cosine squared x is 1 plus cosine 2x over 2. Okay, keep using those until you get down to an odd power of cosine. And when you do, go back and use this one. Okay, all right. A lot of blah, blah, blah. Let's see how they actually play out. Okay, now, here we have the first one, example 1, top of page 533. I can't read from that far away, so let me get it all out. Okay, let's see. I know it was messy, but it's all right to try to write on this screen. That's easier than writing everything down again. Okay, the key here, look for your odd exponent. This is even, not going to work. This one's odd, that will work. Okay, So what we're going to do is rewrite this, if I can get it to do, rewrite this as the integral of sine squared x cosine fourth x times sine x dx. All we did was break one of these out and put it with the dx. That left two of these and of course four of those. We haven't changed anything. Okay, now next step, let's get that sine squared into cosines. Okay, or cosine squareds actually, that would be 1, and there I don't know why it does those lines like that. 1 minus cosine squared x. That's what sine squared is. Remember your Pythagorean identities. This is multiplied, there it did it again, cosine again, fourth x times sine x dx. I'll try to write slower and see if that will make it stop. Alright, so let's take that integral. 1 times cosine fourth is going to be the integral of cosine fourth x. I'm going to split this and make it times sine x dx minus the integral cosine squared times cosine fourth is cosine sixth, I didn't do it, did I? X times sine x, oops, dx. I don't know why it's doing that. Okay, now for both of these, what we're going to do is let a good old u substitution here. Let u equal cosine x. Okay, the innermost part of the most complicated part of the problem. Most complicated part is raising to the fourth power. Innermost part of that is cosine. Then let most of it followed by then du is equal to minus sine x dx. Okay, wait, I've got to get more water. I don't know why I get so dry. Part maybe the ceiling fan being on, but I don't know. Okay, so that's going to go for both of these, by the way. So what does that first integral become? First integral becomes the integral. Now we're dealing with u's and we don't have limits on these, so we're okay with that. We're going to have a minus because we have a sine x dx, not a minus. We'll actually just do that. That's easier. The minus du is going to be here. So this is going to be, cosine is your u, so this is u to the fourth times, and the sine x dx is minus du. We put the minus out here. This is just du. Minus, okay, I have a feeling that's going to become plus because of the very thing we just said. Du is going to be, so that's going to be a plus. The integral of cosine 6 is u to the 6. Sine x dx is your du, or minus du, but we've already taken care of the minus du. So this is pretty easy to do. This is going to be, I don't know why it did that, this will be minus u to the 5th over 5 plus u to the 7th over 7. Yeah, if I slow down it seems not to do it as much. And we're going to write our plus c here, but then plug in what u is. U is cosine x, so this will be, I'm going to reverse the order too. This will be cosine 7th x over 7 minus cosine to the fifth x over 5 plus c. I don't know if the book changed the order of that or not, but let's see what they got. They started with minus cosine fifth x over 5 plus cosine seventh x over 7, which is what I got, plus c. So that's perfectly correct. Now I wish I knew a way to erase all that. I don't. So we're just going to have to let this show up in the background. That's why they have sort of light colored pen, light pen. So because you expect to use the power rule with du equal cosine x, save one sign factor to form du and convert the remaining sign factors to cosines. So you get everything in terms of cosine except for that one sign, because derivative of cosine is minus sine dx. Okay, so that's why we did it, and this is what it becomes then. The sine cubed becomes a sine squared. Cosine fourth stays cosine fourth. That one sign you lost here you put with the dx, and that becomes your du. Ultimately it will. Well, that sine is 1 minus cosine. Sine squared is 1 minus cosine squared. Excuse me. Times cosine to the fourth times your sine x dx, which is going to be your du. And that would be the integral of cosine fourth when you multiply that through, minus cosine 6 when you multiply those two through. And then you have an x dx, sine x dx at the end. Alright, I think when we finish this problem I've got to go clear my head because I'm having trouble breathing. So this is what it came out being: integral of cosine fourth x sine x dx minus the integral of cosine sixth x sine x dx. Okay, and a simple u substitution will work, though they're not doing a simple u substitution, they're doing it without saying that. I find it easier to say the u. It's just easy to do. If you prefer the way they do it without what they did, because the derivative of cosine is minus sine, you wanted a minus in here, so they put a minus out there. And this already had the minus there, so you just drug that in back into here. Okay, that's okay. And this will be cosine fifth x over 5 with the minus sign up front, cosine seventh x over 7 with the plus sign up front, plus c. And there's your answer. Okay. Let's see, how are we doing? We started at 11:30, so we've gone more than an hour and a half now, and we've got less than an hour and a half to go. So this isn't a bad time to take a quick break. I just need to go clear my head. So let's pause the recording here. Oh, I meant to say this before we got started. Monday's class, if any of you were looking for that on the YouTube videos, the Screencast-O-Matic just kind of lost itself somewhere there. I went to save the program like I always do, and it just kind of disappeared. It just disappeared. I tried everything I could think of to get it back. I couldn't get it to come back. So I couldn't load that to YouTube video. So what I tried to do was leave the YouTube videos from probably last fall is the last time I taught Cal 2. And I left those out there. They probably won't match up perfectly, but most of the stuff will be fairly similar. Okay? So if you had looked for that, that's why. So you have to go up to the top part of the YouTube video link and find the sections you were looking for there. Alright, so hopefully this time it won't lose it. Okay, so I'm going to, alright, I just need to do a sound check. Can someone hear me? Anybody? Let me know if I'm audible. Somebody. Hello? Can anyone hear me? Sometimes this microphone goes out and I can't tell because I don't hear anything back. Please, I need to know if my microphone and...
I can hear you.
Good. Thank you so much. Thank you so much. Appreciate it. All right. I started the recorder again. Maybe I shouldn't have started quite that soon, but I did. I was starting to say, here's Wallace's formula. I just realized they skipped two exercises before that. So let me go back a slide if it'll let me do that. Okay. We need to do examples 2 and 3 first. Okay. So these will be done on the whiteboard. Okay. Now I've got to fiddle with the whiteboard again because when we changed the PowerPoints, it changed all this around. Now it left the whiteboard in the right place, but it left the taskbar in the wrong place. Okay, so let's do example 2. Oh, my ink pen and my stylus look very similar. Okay, here's example 2. Okay, now by the way, even if you don't have a book, you can go to larsoncalculus.com. You don't need any codes or anything else to go there and see an interactive version of this type of an example. And here's what we're supposed to evaluate. Now this is a definite integral going from pi sixths to pi thirds, not going very far on the x-axis or whatever your independent variable is, yeah, x. And here's what we've got here. Cosine cubed x divided by the square root of sine x. Okay, that's a pretty ugly x, isn't it? Dx. And you might say to yourself, this doesn't look anything like the type of problems we were working, does it? Well, in reality, it's not far off. First thing to do is rewrite it so it looks better, okay? And here's what I mean by that. It's the integral from pi sixths to pi thirds, okay, of cosine cubed x times sine. Remember, I don't like having things in denominators if I can help it. Sine to the negative 1/2 power. That's what it means, 1 over square root of sine. Square root of sine is sine to the 1/2 power, and having in the denominator make it negative 1/2 power. And then you have a dx. Now, remember what our rule was? If one of those exponents was odd and positive, the sine exponent doesn't qualify on either count. It's negative and fractional. Okay, so it's not odd, it's not even, and it's not positive. Okay, the cosine, however, that 3 is odd and positive. So that's the one we're going to work with. So what we're going to do is separate out one of those cosines. So we're going from pi sixths to pi thirds. Yeah, get out of there. Okay, times cosine squared x times sine to the negative 1/2 x times cosine x dx. Barely squeezed it all in there. All right, let's go back to the start here, and this will be, I'll write down all the steps. I was starting to skip a few, but let's write them all down. integral from pi 6 to pi thirds of, now this time we're going to take that cosine squared and write it in terms of sines. That would be 1 minus sine squared. Cosine squared is 1 minus sine squared. And that's multiplied by sine to the minus 1/2 x times cosine x dx. I get tired of writing that, but okay. One more step before we actually do integration, and that would be the integral from pi 6 to pi thirds of, now let's multiply these together. This will be a sine to the negative 1/2 x, no, x is not up there. Okay, for some reason, okay, let's do that. Alright, I'm going to try to do some things here. Yeah, that's what I want to do. Okay. The x is down there. Sine to the negative 1/2 power of sine x minus, when you do sine to the 4/2 times sine to the minus 1/2, that would be sine to the 3/2 x. Does everybody follow that? Okay. Now, I'm trying to get my pen to come where it needs to be. Okay, there is our thing, and then we still have our cosine x dx. Now we finally get to get rid of that. Alright, what's the most complicated thing here? Those signs to fractional powers, of course. So what's the innermost part of those complicated things? Sine. So that's going to be our u substitution. Let u equal sine x. Now you don't have to do this if you don't need it. Then du is equal to, what's the derivative of sine? Cosine x dx. And that's exactly what you've got here. So let's rewrite that first integral. Now, I'm not going to put the limits on it yet because we've got to go back and change those. That's doable. This will be u is sine, so this would be u to the minus 1/2 minus u sine to the 3/2, okay, and then the cosine x dx is du, okay. Now let's fiddle with our limits now. What in the world, when x is equal to pi 6, does anyone know what sine x is? Sine of pi 6. I hope you do, and you're just too shy to say. 1/2. What is sine of pi thirds? Square root of 3/2. So when you have a definite integral with limits on it, and you make your u substitution, usually it's a good idea to go in and substitute what the values are there. So now you don't have to come back and plug back in x's. You can just evaluate your u's. So let's do that. Let's take the antiderivative of u to the minus 1/2. Well, that will be u to the positive 1/2. divided by that new exponent 1/2, which will be dividing by 1/2 is the same as multiplying by u, minus u to the increase this by 1, that gives you 5/2, and then you divide by 5/2, which is the same as multiplying by 2/5. Okay, and then we'll evaluate this from 1/2 to √3/2. That's going to be the messy part. Oh, yuck, will that ever be a messy part? Okay. Okay. And it will be. Okay. I was trying to see how they left it, but they leave it in a mess. Okay. I was wondering if they had some simpler way of writing this. This would be 2 times square root of 3/2 to the 1/2. So let's just leave it like that. 2 times the square root of 3/2 to the 1/2 power minus 2/5 the square root of 3/2 to the 5/2 power, and then we're going to do a minus a 2 times 1/2 to the 1/2 power. Minus a minus is a plus 2/5 1/2 to the 5/2 power. And you don't have a plus c because you had definite integrals. Okay. Now, I seem to have a problem with something here. Okay. The first part they leave as it is. The rest of it is just getting it in the same form they have. That would be 2 times the square root of 3/2 to the 1/2 power minus 2/5 the square root of 3/2 to the 5/2 power. Now, they do some monkeying with this, and I'll show you what they're doing here. Minus. Okay. This 2 is to the 1/2 power. This 2 is to the first power. So that's the same as the square root of 2. 2 to the 1/2 power. This one, the denominator, is to the 1/2, so it's a minus 1/2. So you got a 2 to the 2/2 power divided by a 2 to the 1/2 power, and that's 2 to the 1/2 power, or square root of 2. And we'll do the same type of thing with this. This is a this 2 up here is to the 2/2 power. This 2 down here is now to the 5/2 power. So that will leave you a 2 in the denominator, because it's 2 to the 4/2 power, which is 2 squared, so it's a 4 in the denominator. So that's just going to be a plus, I think, 1/20th, if I did it right. Let me see if that's right. No, 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 that's not right. This is 4/2 power in the numerator. No. Yeah. Where is, there it is. This is 2 to the 2/2 power up here and a 2 to the 5/2 power down there. So I didn't do that right. I don't think my, okay. Let me try this again. Okay. Now, let me go back and try that again. Let me wipe all that out. Plus, okay. Okay, where are you, pen? There you are. Okay. 2 to the 2/2 in the numerator, 2 to the 5/2 in the denominator. That'd be 1 over 2 to the 3/2 in the denominator. So it'd be 1 over 5 times 2 to the 3/2 power. No, 2. No, yeah, 3/2 power. Okay. How did they leave it? All right. Phew, goodness gracious. They got that first part. Let's see what they did with the second part. Okay, if you square the numerator and denominator of, no, that's not what you want to do. Multiply, let's try this. Multiply this by the square root of 2, okay, which is 2 to the 1/2. Multiply this by the square root of 2, which is 2 to the 1/2, okay? Now, that would leave this as, I don't know why I'm wasting so much time in this, square root of 2 up here, and down here this would be the square root, this would be 2 to the 1/2 times that, 4, 20, okay. That would be 20 in the denominator. I think is what I had earlier too. Why in the world did they do the square root of 32 over 80? Okay, I don't know. They multiply the numerator by the square root of 16, which is 4. Yeah, and 4, yes. So I don't know. That doesn't make any sense. I don't know why they left it in the form they did. I spent all that time trying to rationalize it and make sure I had it right, and I did. But they just chose a really stupid form to do it. So let me go to my calculator and let's make sure they got the same thing. Oh, this is a mess, but it's a doable mess. Okay. I'm using a phone, so I have to turn my phone to the, oh wait, I have to hit the calculator first. Turn that to the side. All right. And that would be, yuck. Let's first do the square root of 3. That sure didn't do right. Okay, let's try that again. The square root of 3, yeah, that's better. Divided by the square root of, no, divided by 2 equal, and then take the square root of that, okay, and then multiply that by 2, and multiply that by 0.4. This is going to be easier than doing the way they did. And multiply that by square root of 3 squared would be 3 times the square root of 3. Okay, I think I got them all. And then divide that by the square root of 32. Okay, minus, goes on forever, doesn't it? The square root of 2 plus the square root of 2 divided by 20. No, it came out something really squirrely. And it was just trying to work this. Phones don't make great calculators. Sorry. So I'm not going to mess with that anymore. Let me get something for my throat. All right. I know their answer is right. I just not going to fiddle with trying to find it anymore. Why they chose such a weird way to express it, I don't know. Let's move on to example 3. Okay. Now this is one they talked about but didn't do anything with. Okay. So let me come up here and where in the world? There it is. Okay. All right. All right. I don't know why it's doing that. I didn't even touch the pad and it starts drawing. Okay, let me try it again. Here we have the integral, indefinite integral, of cosine to the 4th x dx. Now remember what they said, if neither the m or the n was even, was odd, then you have to get them into powers of your cosine squared. And you don't have a sine squared yet, powers of the square function. So I know what I'm trying to say, I'm not saying it very well. So this is the same as the integral of cosine squared x squared dx. Okay. Now, if you go back and check that trig identity they introduced to you, this is 1 plus cosine of 2x divided by 2. And that is squared dx. All right. Now, if you do have your book, you can flip back a page and see, actually a little more than a page, back to 532, and you'll see that cosine squared is 1 plus cosine 2x over 2. Okay, so that's what we did. But we had that squared. Now, I think I'm going to get rid of this book. It's way too heavy to be holding in my lap any longer. All right, now I'm going to do a couple of things with that, and maybe some of them at once, and hopefully you'll follow this okay. What this is equal to, okay, that denominator 2 is squared, so that's a 1/4. So I'm going to pull out the 1/4. Okay, and then I'm going to put my integral sign. Now I'm going to expand, square this binomial. Well, you square the first term, 1, plus twice the product of the 2, plus 2 cosine 2x, plus the square of the last term, which is cosine 2x, cosine squared 2x. Okay, and then that's multiplied by your dx. Okay, I hope you followed that chain of reasoning there. All right, now this is actually three integrals, and you can do the first two. Okay, we'll come back and do those in a minute, but let's focus on the third one. Okay, so I'm going to write down, if I can get my pen to come back down here where it needs to be. Okay, this is going to be 1/4. I'm going to break it into integrals. Now this one I'm going to keep the first two together. 1 plus 2 cosine 2x dx. Okay, I'll keep those two together because they're easy to do. Plus, now this is all times the 1/4, so don't forget that. Okay, now the next integral here is going to be another cosine squared, only this time the argument is 2x. Well, what is cosine squared? It's 1 plus cosine 4x over 2. Okay, dx. Okay. All right. Now, I think I'll bring that 1/4 back into play here. Okay, integral of dx of 1 dx is just x, so that's going to be 1/4 x. Okay, plus 2 over 4 is 1/2. Okay, I'm going to write it down, though I'm going to change it in a minute. And then the antiderivative of cosine is sine of 2x. But then the chain rule makes us divide again, so that changes the 2 back to a 4 again. Sorry about that. Okay, we're going to wait and do our plus c's at the end. So then we're going to have a plus. Now you got a 1/4 out here, and you got a 1/2 in here, so that's going to be a 1/8 here. And the antiderivative of 1 dx is going to be x. So there's 1/8 x. And then the antiderivative of cosine 4x, remember I'm going to put the 1/8 down here because it's still there, that 2 and that 4. Okay, and the antiderivative of cosine 4x is sine 4x over 4, which now makes this a 32. Okay, and then we'll finally have our plus c. Now 1/4 x plus 1/8 x is 3/8 x plus 1/4 sine 2x plus 1/32 sine 4x. Plus c. Now, if my memory's right, the book chooses to write this in a rather strange form. No, actually, it leaves it like that. 3/8 x plus, they put sine 2x over 4, that's fine, plus sine 4x over 42 plus c. Now, it says use a symbolic differentiation utility to verify that. Well, I don't have a symbolic differentiation utility, so I'm not going to do it. But it says in example 3, when you evaluate the definite integral from 0 to pi halves, which they didn't do, but if you had, you would then obtain the 3/8 x, when you plug in pi halves for the x, you would round up with 3 pi over 16, and then all the rest of your evaluations, when you put pi halves m for x, 2 times pi halves is pi. That's going to be sine of pi is 0, and sine of 2 pi is 0. So everything else disappears. So you wind up with 3 pi over 16. So it says, note that the only term that contributes to the solution is the 3/8 x. Okay? If you had evaluated this from 0 to pi halves. Okay. Now that observation is generalized in the following formulas developed by John Wallis, who lived from 1616 to 1703. Now that's not super important what I'm mentioning there about his years of his life, except for this. Well, let's go and clear this out of the way. So we go back to the text. Seems like we're losing people here. Okay. And get back to current slide. And that was example 1. Okay, here's Wallis's formula. Now, the reason I pause here and the reason I mention the years that he was there, he was a very good mathematician. And he must have been a pretty good human being too. I'll explain that in a minute. He did much of his work in calculus prior to Newton and Leibniz. He influenced the thinking of both of those men. He's also credited with introducing the present symbol for infinity, that sideways 8 that you know. So he was a really top-notch mathematician. The one reason he's probably not known any better than what he was, when it says he influenced the thinking of Newton, he was chair of the math department at Cambridge. I think I've got this right. When Newton came in as a student, Newton was obviously totally brilliant. I mean, way beyond brilliant, way beyond anybody else's perception of physics and math. And Wallis stepped down to allow Newton to become chair of mathematics. He had seniority. He had every reason to hang on to his position for dear life, you know, except he chose not to. He recognized Newton's brilliance, stepped down, and let him become chair. So that's why I say a quality individual as well. So John Wallis, these are his formulas. If n is odd, and the problem we just did, the n was even, and n also greater than or equal to 3. Doesn't work when n is equal to 1. But if n is odd and you're just integrating from 0 to pi halves, it has to be those limits. Cosine to the nth x dx, what you do is start with n minus 1 over n. So that would be 2 over 3. And then you keep going. Okay, I'm sorry. You start with the smallest it could be, if n was 3. And then you go up until you get to n minus 1 over n. So if that were, pick an odd number. Anybody, give me an odd number. Say again? Did someone answer? Give me an odd number. Anybody? Hello? Anyone out there? Give me an odd number. 7. Excellent. Thank you. Okay. So n equals 7. So you're trying to integrate from 0 to pi halves cosine to the 7th power of x. Cosine, 7th power of cosine of x. dx. So where would you start? 2 over 3 times 4 over 5 times 6 over 7. Once you reach that 7, so notice what you did. 2 over 3, 4 over 5, 6 over 7. 2, 3, 4, 5, 6, 7. Okay, you're just counting up like that. Those are your fraction. Okay, stop when you reach 7. Multiply those two together. And you get, I don't know, 48 over 105 or something like that. That's your answer. You don't have to do any integration. You don't have to do anything else. Now, if n was even, like the one we just had, 4, then, and if you're integrating this from 0 to pi halves of cosine fourth, then it would be 1 over 2 times 3 over 4. Stop there. That's 3 over 8 times pi halves. And that's exactly what we did right at the beginning. 3 over 8 times x. Your x is your pi halves. You're done. Okay? Those formulas are also valid when cosine nx is replaced by sine to the nth x. Do the same thing with sines. Okay. Rather remarkable, and maybe not too remarkable if you think about why sines and cosines are the same. If you think about the shapes of sine and cosine, they're identically the same. So the area under them, or the integration from 0 to pi halves, would be the same. Cosine starts at 1 and goes down. Sine starts at 0 and goes up. But the area under those are exactly the same. Okay. And if you're only going to pi halves, then that's where you stop. Okay. Okay, that was Wallace's formula. Now we're moving to integrals involving powers of secants and tangents. Okay. Here are the guidelines. These are on your page 535. How are we doing on time? Yeah. Okay. The guidelines below can help you find integrals of the form of the integral of sine to the mth x times tangent to the nth x dx. So here's what you use. When the power of the secant now, is even and positive, save a secant squared on the outside, because this tangent, the derivative of tangent, is secant squared. So you want the secant squared x dx to be your d-tangent. Okay? So that's why. So when the power of secant is even and positive, save a secant squared on the outside, convert the remaining factor to tangents. You're going to have some remaining secant to some even power and convert that to tangents. Okay? Then expand and integrate. So this is how they're showing that. Secant is to an even power times tangent to any old power. It doesn't matter what. N can be, it doesn't even have to be positive. It could be negative, it could be positive, it could be a fraction, it could be a decimal, it could be any n. Before we're saying n's usually, okay. Now, the secant squared, you pull that out, and that's raised to the k minus 1. Why k minus 1? Because you pulled one of those secant squares out. Okay? And then this is tangent to the nth, and this is a d-tangent, is what it's going to turn out being. Well, this is 1 minus tangent, 1 plus tangent squared x. That's what secant squared is. That raised to the k minus 1 power, and then you multiply that by tangent to the n, secant squared, which is your d-tangent. Okay, and from there, everything over here is in terms of tangents, everything over here is d-tangent. Okay, now, when the power of tangent is odd and positive, tangent odd and positive, save a secant-tangent combination. Okay, secant-tangent factor, convert the remaining factors to secants. So if this was a secant to the m could be any number, Positive, negative, fraction, decimal, it doesn't matter. But the tangent has to be an odd positive power. Okay? So you express that as 2 times some k plus 1. That makes it odd. And you pull one of the tangents out, but also pull a secant out. So you have a secant tangent. That is going to be your derivative of a secant. So now you have a secant to the m minus 1 because you pulled the secant out, and tangent of 2k because you pulled the tangent out. But now do the tangent squared on the inside and the k on the outside. Change this tangent squared to secant squared. And tangent squared is secant squared minus 1. That's raised to the kth power. And this is your secant m minus 1 because you pull that out. Excuse me. I'm so sorry. Oh, man. Okay. Now, this is all so blah, blah, blah-ish with all the m's and k's and everything else. But this you expand. Raise that to the kth power, and if you need to, we'll go over Pascal's triangle to show you how easy that can be. And then multiply this part times secant to the m minus 1. What you do then is add whatever power you get here from raising this to m minus 1. You get secant to that power, and then the second one will be to secant to the m minus 1. And then this is the derivative of secant. Okay. Now, when there's no secant factors at all, okay, and the power of tangent is even and positive, you then need to convert a secant squared factor to a tangent squared factor to a secant squared factor, okay, then expand and repeat as necessary, okay. Now, in tangent is even, there are no secant factors, tangent is even, okay. Pull out a tangent squared, okay. Now, this then will be a tangent to the n minus 2. This will be a tangent squared, which you can convert to secants as secant squared minus 1. That's what tangent squared is, okay. Now, what you have now is tangent to an even power, secant to an even power, and this will be tangent to an even power, okay. This form, you can use the secant tangent thing we just did, okay, and the remaining form, you can just keep doing the same thing to it until you use up all your n's. All right, that's a weird way to express it, but that's really what happens. When the integral is of this form, secant to the mth x, where m is odd and positive, then do integration by parts. Whoa, we just did that, didn't we? And we really did one similar to this before. Remember, m is odd and positive, so pull out just the secant squared, which is the derivative of tangent, and so that be your dv, and then whatever secants you have left over, that will be your u, and then you proceed like we did in an earlier problem. Now, when the first 4 guidelines do not apply, try converting to sines and cosines, okay. Sometimes I do that a lot sooner than this, okay, but that's what they suggest. All right, so let's move on to example 4. Here we have it. All right, now I'm going to try doing this as we did earlier, writing on the screen here to keep from having to copy it. Okay, so this is, first thing I do, write it into a simpler form. The integral of tangent, there, I don't know why it does that, tangent cubed x times secant to the minus 1/2, there it did it again, minus 1/2, and they did another one, okay, x dx. Okay. Now, all right. So here's what the deal is here. Pull out okay. Let's go back real quickly to see here. This would be when tangent is odd and positive. This is the one we're using here. Save a secant tangent factor. So that's what we've got to do, is pull out a secant tangent factor. Ooh, that's going to be sort of messy, isn't it? Okay. I don't know, let me write it down here because this is going to take a while to write. It's going to be the integral of, if you pull out a tangent, you're left with tangent squared. Pull out a secant, you're left with secant. You see, that was a minus 1/2, now it becomes a minus 3/2 x times secant x times tangent x dx. So you pulled one of these tangents from here to go down here, one of the secants here to go there, leaving you secant to the minus 3/2 power. Now, what that gives you, if you remember your Pythagorean identity here, tangent squared is, look at that, secant squared x minus 1. Okay? Times a secant to the minus 3/2 x times a secant x tangent x dx. Okay, I don't know why those things happen. I wish I did. All right, now we're going to multiply. This is tangent to the 4/2 times a tangent to the negative 3/2. That will be secant, I said tangent, secant to the 1/2 x minus secant to the minus 3/2 x times secant x tangent x dx. All right. Excuse me just a minute. I am so sorry. I'm feeling actually almost lightheaded. I don't know what's going on. Okay. Now this is your, basically your integrand, and you just do a simple u substitution. Let u equal secant x. Then du, and remember what's the derivative of secant x? Secant x tangent x dx, which is exactly what we've got there. So now your integral is the integral of u to the 1/2 minus u to the minus 3/2 times du, because this thing here is du, this thing here. Okay, now that's a simple integration to do, pretty much. It's u, the same base, increase the exponent by 1, so 1/2 plus 2/2 is 3/2, okay, times 2 over 3, or divided by 3 over 2, minus u, and increase that by 1. That's minus 3/2 plus 2/2 would be a minus 1/2. And then you divide by the minus 1/2, which is the same as multiplying by 2. Okay. Then you do your plus c. Okay. I'll tell you, I'm not feeling very well at all. Make it 20 more minutes and we'll be done. Okay, sorry about that attitude, but wow. Okay, now we can go and plug in our answer. That is the answer here. So this will be, I'm just going to put the equal sign here, 2/3. U is secant x, so that would be secant to the 3/2 power plus 2, and you can put it to the minus 1/2 power or put it 1 over square root of secant. I don't care which one you do. Since they had it minus that, you could put it like this, over the square root of secant x. You don't have to, but that's how they had it in the original problem. Okay, plus c. Now let's see how they left it. Example 4. 2/3 secant to the x to the 3/2 power, and they wrote it on the outside, that's fine, plus 2 times secant x to the negative 1/2 power, which is exactly what we had, plus c. So, yep, same answer. They're going to write it differently. I wish I knew how to erase this. I might be able to do it by doing this. Nope, it's not doing. Okay, I thought that might work, but that would be a long process anyway. So let's see what they get. Excuse me, because you expect to use the power rule with u equals secant x, that's really looking ahead. You save a factor of secant x tangent x to form du, which is derivative of secant x is secant x tangent x, and convert the remaining tangent factors to secants. So, oh my goodness. Yeah, they did it right. I would have put the tangent cubed first, but they did the secant to the negative 1/2 tangent cubed. That's just a rewrite. And then pulling out one secant leaves you secant to the minus 3/2. Pulling out a tangent leaves you tangent squared. There's a secant, there's a tangent dx. Okay. Whew. Get rid of all that stuff. And that would leaves you secant x to the minus 3/2, and they're putting the exponents there rather than by secant, which is fine. Okay, times, and the tangent squared is secant squared minus 1, which is what we did, and then your secant x tangent x dx, we'll hang on to that to be your du. And that then gave you, when you multiply secant to the 2/2 power times secant to the 4/2 power times secant to the minus 3/2 power, that leaves you secant to the 1/2 power minus secant to the minus 3/2 power, because that's just multiplied by 1, and then the secant x tangent x there. Now I would do the u substitution. They don't. It's okay, but it's the same thing we were doing. It's this thing, secant x, increase the exponent by 1, and then take this and divide by that, which is multiplying by the reciprocal of that. And then you have a minus secant x to the minus 3/2, will increase that by 1. Secant x, now it goes to minus 1/2, multiplied by its reciprocal, which is a minus 2, so that changes the minus here to a plus 2 here. And there's your answer. Okay, so by not doing the U substitution, you do save a few lines, but it's sometimes not completely clear how they did it. I like doing the U substitution, but that's up to you, however you'd like. All right, let's see if they do example 5. No, they don't. So let's us do example 5. Now, this has nothing to do with this class specifically, but it has to do with maybe a few people in the class. I just happened to see Kira's picture there and her name there. I know she had requested that we run Physics 218 this summer, and as far as I know, they put it on the schedule. If they haven't, let me know. But I did have another student who indicated he might be taking it in the fall. So if any of you are interested in taking modern physics, which is Physics 218 this fall here at Lawson, it'll be offered remotely. Dr. Bryant will be teaching it. He's taught it before. I think you'll find it a pretty interesting and class, and it is required for those who are graduating in a pre-engineering here. So if you want to sign up for that, it is out there on the schedule now, or at least I hope it is. So anyway, just wanted to say that before I forgot it, since this is my last chance to see any of you for a while. Okay, this is example 5. Now it says my internet connection is unstable. What a terrible time for that. Could y'all hear me when I was talking then, or did that get garbled? Anybody?
You cut out towards the end.
Okay. What happened, I had a little message come up saying my internet connection was unstable, so I quit writing, just kept talking, and that's what cut out. So sorry about that. Okay. Now I think we're, down to example 5. Let's try example 5, if I can get it to come up here. This is the integral of secant to the 4th x, no, 3x, sorry about that, 3x times tangent cubed of 3x dx. Okay. They're adding a new little wrinkle here. Yeah, they're having us do something we talked about that we probably haven't done, but also adding another wrinkle, which I found an interesting concept to do. Why don't you do one thing at a time? But they're not. Okay. So now if you flip back a couple of pages, no, one page, and what were our guidelines for secants and tangents? First, if power of secant is even and positive, that it is, stop right there, we can deal with this. Okay, so if that's the case, we want to pull out 1 secant squared and put with the dx, because that now is the derivative of tangent, and then get the other secant squared in terms of tangents. Okay, multiply by the tangent we already have, and you'll be okay. So let's do what they say then, and this was an indefinite integral. That would be the integral of secant squared 3x tangent squared, no, tangent cubed 3x times secant squared 3x dx. Whew. Okay, now let's come back over here and make this the integral of, now since we have a d-tangent here, let's get this secant in terms of tangent, and what would that be? hopefully you remember, it's a tangent squared 3x. I don't know what it's doing. It's losing its mind here. Oh, I see. Now my whatever you call this, Zoom is disconnected. So I'm going to stop the recorder now.